Is there a serious problem with scientific integrity in the US government's handling of climate change and climate and energy policy? What does scientific integrity mean anyway? And how would you recognize breaches of scientific integrity? Tonight, Kenneth Happala, president of the Science and Environmental Policy Project, joins us to discuss these and related questions raised in his article, Comments on Federal Scientific Integrity, on the Cornwall Alliance's blog. Well, thanks for joining us tonight. We'll welcome Ken in a moment. First, I want to alert you to a great opportunity to become part of the solution to the fake crisis of climate change. The Cornwall Alliance will gladly send you, absolutely free, 10 copies of any one of over a dozen different educational tools as our way of saying thank you when you make a 100% tax-deductible donation of any size and request it. And then you can give those away to friends, teachers, or colleagues so they can learn too. For a complete list of the resources we're offering, go to this post on our Facebook page or enter cornwallalliance.salsalabs.org/livestream does federal climate science have an integrity problem into your browser. That might be hard to get. If you just simply go to our Facebook page and run down a little bit, you will see the post about this. That might be the easiest way for you to get there. Of course, if you receive Cornwall Alliance's regular email newsletters, you'll have received one that shows you exactly how to do this. To request your 10 copies of any of these publications, just go to cornwallalliance.org. That's cornwallalliance.org. Click on the donate button, and as you complete the donation form, in the comments field, write promo code 21-09 and the title you want. Well, now we welcome Ken Happala to our program, From the Stacks. Ken, thanks so much for joining us. Ken is the president of the Science and Environmental Policy Project. But Ken, I've learned from Robert Bryce, who's probably someone you know as well, major writer on energy physics, energy engineering, energy policy, and so on. From his podcast, I've learned that it's always the most interesting just to ask us to introduce himself rather than introducing you myself. You know yourself a lot better than I do. So tell us about yourself, your background, how you came to be doing what you're doing now.
Thank you, Kelvin. After military service, where I served as a captain in the artillery, I went to graduate school in economics. And after passing my doctoral exams, I taught and did energy, economic modeling. And in teaching, I began to realize that much of what we taught was speculation. We didn't have the evidence supporting many of the theories that were in the textbooks. And this was very frustrating for me. Subsequently, through modeling, I was engaged under a federal contract to review the energy models that the federal government was using, particularly the ones on natural gas. And as I went through the code, I got the code for the natural gas model, I realized that there were logical errors, significant logical errors in the code that made the model useless. You couldn't make any type of reliable prediction from it. And this was being done. We had all sorts of grand predictions that within a few decades, the US would run out of oil and natural gas. This created a tremendous amount of frustration for me, and I spent a great deal of time reading on other issues on how do we know what we know? How uh, can we be comfortable that our knowledge is solid? And after several years, there was no one book that I considered to be particularly good on it. And probably the best series of books was the writings of Bertrand Russell, who was a logician and a mathematician in England, and who was considered to be very left wing. But his
Yeah.
writings were brilliant and very clear. Uh, some years later, and I went into doing other things other than economics because I was dissatisfied with it. Some years later, I came across the writings of Richard Feynman, and I wished I had seen those many years earlier because it would have
Yeah.
saved me a lot of time. But then again, if I had seen them many years earlier, I would not appreciate how brilliant he was in summarizing the major problems that we have to look at in order for science to advance. And you have a little film clip that pretty well covers it, except I would add certain things to it. But our biggest issue is how do we know what we know, and how we know, and more than that, how do we know that something else we think about is wrong? And
Yeah.
if you want to look at the history of the last 500-600 years, we can start off with the Earth, the concept that the Earth was the center of the universe. There was nothing wrong with that concept for hundreds or thousands of years. The Phoenicians were able to sail the Great Pacific, not knowing that the Earth revolved around the sun. Our early explorers didn't know that the Earth revolved around the sun. Their concepts worked, but it wasn't until we made careful examinations of the movement of the planets that the concept that the Earth-centered universe began to fall apart. And it was a huge controversy that took place over several hundred years between those who insisted the Earth was the center of the universe and those who insisted that the sun was the center of the solar system.
Yeah.
And we have the issues that came very strongly during the early 1500s with Galileo and others, Kepler particularly, on one side, and many others who refused to accept that the Earth could, the center of humanity could not be the center of the universe. Of course, this all fell apart with the telescope. Once we had the telescope, you could see the movement of the Mars of Jupiter, for example, forming an orbit around the planet. And that is the key to the advancement of science, as far as I can see. And that is that as new information comes along and challenges the ideas of the past, we have to thoroughly test that information. But if it's solid, then we have to change our concepts and change how
Yeah.
we think about the world.
Yeah, we're actually going to show that clip from Richard Feynman on the key to science shortly. First, though, I want you to tell us a bit about the Science and Environmental Policy Project. Who's involved? What are its aims? How does it work? How did you become involved in it? And where can people learn more about it?
The Science and Environmental Policy Project, SEP, was formed by Fred Singer in 1990. And he attracted a very uh, good board of very solid scientists, including Frederick Seitz, who was for 10 years
Hmm.
the head of the uh, National Science Foundation. I'm
Hmm.
sorry, National Academy of Sciences.
Yeah, right.
And the uh, the purpose was to start to challenge many regulations and laws put out as policy using the scientific method. It doesn't, can we test whether the foundations of these laws and regulations are scientifically valid? Uh, the size of SEP has changed over the years. Frederick Seitz passed away a little over 10 years ago. Fred Singer passed away a year ago.
Yeah.
And I got involved about 10 years ago. I
Hmm.
had been the president of a science society in Washington, the oldest one in Washington, as well as doing other things principally unrelated to science, except some modeling.
Hmm.
The For 10 years, I've been the principal compiler of our weekly newsletter called the Week That Was, and that goes out about 50 times a year. Um, we're a nonprofit, 501c3, uh, and we have a board of 8 members, nine members, to include Willie Soon, who's a expert in astrophysics, Tom Sheehan, uh, who worked for years for the government, particularly in renewable energy, is a
Yeah.
PhD in physics from MIT, and others. We put out this weekly bulletin, and it's reviewed by 3 to 5 physicists each time.
Hmm.
So I'm pretty confident that the scientific basis is solid.
Yeah, I find the week that was an absolute treasure trove. Every single issue that comes out, you guys, uh, you really bring together a huge amount of what's been published in terms of the significant discussions on especially climate change, but a variety of other subjects as well. And you provide links right straight to the original articles and the like. So it's a hugely helpful resource to me in leading the Cornwall Alliance for the Stewardship of Creation. Well, Ken, in your article, and again, the title of that is Comments on Federal Scientific Integrity, which is on Cornwall Alliance's blog, which people can see right there in front of us, right there. In there, you start off with a discussion of the scientific method. And how would you define the scientific method, Ken?
It's an ongoing process of establishing new ideas and correcting errors of the past. And we do that by comparing the concepts with new physical evidence as it is uncovered. That's why I consider the idea of the telescope so important as an example, because that put the clarity that the idea that the Earth is the center of the universe is erroneous.
Yeah.
Um,
Ken,
we
if I can interrupt you for a second, I thought it was significant that what you just said was that we correct the errors of the past while coming up with new ideas in the present. You didn't say we correct the errors of the past while coming up with truths of the present. Now, we hope things are true when we embrace them, but it's significant that your view of the scientific method is not so much one of establishing truth as refuting error. Uh, and I think that stems in part from from what philosophers of science and epistemologists refer to as the inductive fallacy. The problem that you really cannot you cannot prove any universal claim about the empirical world by observation because you've never observed the entire empirical world. Therefore, you can disprove some claims. You can show that some claims were false, but you never arrive at universal truth that way. Is that a fair notion?
Very much so. That's very well put. Uh,
So
we
those
can
who
only
talk about settled science are really misunderstanding scientific method in a very basic way. Is that right?
yes, because ideas change as you get more information. An
Uh-huh.
example relating to climate. In 1979, a panel of experts assembled and came out with what is called a Charney report that
Hmm.
that showed that they concluded that increasing water vapor will occur as you increase carbon dioxide in the atmosphere. Though slight warming from increased carbon dioxide would result in a greater warming from increasing water vapor. This ran contrary to what was being observed in laboratories, decades of laboratory research in spectroscopy, but
Hmm.
no one could tell whether this idea was correct or not correct because we didn't have the evidence.
Uh-huh.
So here we have a good idea, speculation of what may happen if we increase carbon dioxide. Since then, particularly since the 1990s, but also earlier, we've been gathering data on what is actually occurring in the atmosphere.
Yeah.
And what is actually occurring is a modest warming with its greenhouse gas warming, very modest. And this is along the lines of what was shown in experimentation since the 1860s, that carbon dioxide is a greenhouse effect, has a greenhouse effect. Its greenhouse effect is very important, but as carbon dioxide increases above a very small, low threshold level that was never experienced, its effectiveness declines rapidly.
Hmm.
Uh, we are not seeing the amplification that came out of the 1979 Charney report. So the observations and experiments, decades of experiments, correspond with one another and refute
Yeah.
the idea that an increased carbon dioxide would cause a drastic warming. It will cause some warming. There's no question about that, but it's mild. It's modest.
Yeah, you've actually you've jumped way ahead in my outline. I was going to ask you about that very thing, the notion of amplified warming by uh, water evaporation and the collection of water vapor in the atmosphere. So when we get to that point, I'm going to have to just kind of skip over it. You've already addressed that very well. Well, at this point, I would like us just to show that brief clip from Richard Feynman. Feynman, of course, was a Nobel Prize winning physicist and an amazingly fine communicator and educator. And I think an awful lot of physicists would love to have known Richard Feynman. I'd have loved to have known him, but I'm not a physicist. But this has been one of my favorite little YouTube clips for, probably the last 20 years or so. And I think it states really, really well in clear and brief terms what the scientific method is really all about.
Now I'm going to discuss how we would look for a new law. In general, we look for a new law by the following process. First, we guess it. Then we so don't laugh, that's really true. Then we compute the consequences of the guess to see what, if this is right, if this law that we guessed is right, we see what it would imply, and then we compare those computation results to nature, or we say compare to experiment or experience, compare it directly with observation to see if it works. If it disagrees with experiment, it's wrong. And that simple statement is the key to science. It doesn't make a difference how beautiful your guess is. It doesn't make a difference how smart you are who made the guess or what his name is. If it disagrees with experiment, it's wrong. That's all there is to it.
I think that's just brilliant. And I think we could add, he says it doesn't matter how smart you are or how beautiful your guess is or who made it or what his name is. If it disagrees with the experiment, it's wrong. I think we could add to that, it also doesn't matter how many people agree with you. And that just completely destroys all the common claims that, okay, 97% of all climate scientists believe. Well, actually, it's not true. 97% of all climate scientists don't believe any of the crisis catastrophe claims that are going around. But even if 97% did, it wouldn't matter, because the fact is that the actual experiments, observations in the real world, have found that, for instance, the climate models, the computer climate models, grossly overstate the warming effect of carbon dioxide in the atmosphere. And one of the main reasons why they do that is precisely that written into pretty much all of the models is the assumption that you just discussed, that as the atmosphere warms, evaporation will so increase water vapor in the atmosphere, which is the most important greenhouse gas, as to amplify the little bit of warming that comes from the added CO2. What people have forgotten, what that theory forgets, is that when water evaporates, it doesn't just form vapor, it can form clouds, which are droplets of liquid water, and it can also form ice crystals. And those clouds and ice crystals have a very different impact from water vapor. So, what do you think, Ken? Is Feynman's brief statement there a pretty good abbreviation of the scientific method?
Yes, I think it is an excellent abbreviation. I would emphasize, a lot of people, unfortunately, only emphasize the experiment part.
Yep.
Observations are equally important,
But
though
in nature,
observations are more sloppy than a well-designed experiment. But the other point I'd like to make is that what we're seeing by observations of what is occurring in the atmosphere, we're not seeing the evaporation taking place in the tropics increasing significantly. And that's primarily because the assumption of a dramatic increase in water vapor came from a misunderstanding of a important equation in physics that's well established. They confused basically temperature with vapor pressure. And if the air is dry, water will evaporate quickly. But if the air is already with a high humidity, which you have in the tropics, you're not going to have a great deal of evaporation, even if you budge the temperature slightly.
Okay, all right. Okay, so Ken, in your article, your second section is called The Changing Climate. There you emphasize that Earth's climate system has never been in what you call energy balance. Yet fears of catastrophic climate change seem often to hinge on the idea that the climate system has been driven out of balance by emissions of carbon dioxide and other so-called greenhouse gases. What's wrong with that idea?
Yeah. I jokingly say that those who talk about a tipping point should look back at those who talked about a tipping point when the sailors sailed too far from the land. They would tip over the world and fall off. The uh, our climate has undergone tremendous warming and cooling in the past,
Mm-hmm.
and it doesn't reach a point where it continues to amplify. The we came out of we've come out of ice ages, and they didn't stay. The ice ages or the glaciations didn't stay for extended periods. They melted, and then we had glaciation again. This has been over the last 3.5 million years. Before then, the Earth was considerably warmer, and it's probably largely due to orbits that we don't understand, the orbit of the Earth, which we don't fully understand.
Hmm.
The the other thing, again, focusing on carbon dioxide, is that with the atmosphere above even pre-industrial level of 280 parts per million in volume, the increase in carbon dioxide does not have a significant effect on temperature. It only has a significant, carbon dioxide only has a significant effect at very low levels. And this has been both shown, as I said, in experimentation, and it is being confirmed by observations of what is occurring in the atmosphere. And unfortunately, those who promote dangerous global warming ignore what is occurring in the atmosphere. We have greatly increased our ability in the space age of observing what is occurring in the atmosphere, and they basically ignore this space age and the observations made during it.
Yeah. We're going to continue this conversation in just a minute. First, I want to remind all of you that the Cornwall Alliance is giving you a great opportunity to become part of the solution to the fake crisis of climate change. We will gladly send you absolutely free 10 copies of any one of over a dozen different educational tools as our way of saying thank you when you make a 100% tax-deductible donation to the Cornwall Alliance and request those 10 copies of some title. You can then give those away to friends, to teachers, to colleagues, so they can learn too. For a complete list of those resources that we're offering, you can go to a post on our Facebook page, or you can go into the weekly email that we send out to those who subscribed to it. And if you haven't subscribed, I'd encourage you to do that. Just go to cornwallalliance.org and then click on the button for getting updates to get updates about the Cornwall Alliance. That way you can subscribe free of charge to our email newsletter. This is our way of saying thank you for your support for the Cornwall Alliance. And we hope that you'll use this to be able to influence the thinking of plenty of friends that you have about this issue. The other side is, the other side on this controversy is supported by billions and billions of dollars in government spending, plus millions of dollars in left-wing foundation grants and grants from various companies and so on. The Cornwall Alliance depends on on donations from private individuals just like you. And so we would encourage you to support our work in this way. So back now to Ken Hoppala, our guest tonight, the president of the Science and Environmental Policy Project, or SEPP. To learn more about it, just go to sepp.org online. Ken, in the article that we published of yours on Cornwall Alliance's website about federal U.S. government integrity problems in science, you say that let me see here, that there are two parts of physics involved in climate change for which we have no comprehensive theories established by physical evidence. The first of those two parts is fluid dynamics, and the second is the greenhouse effect. Would you quickly define each of these for us, and then tell us why it's so important to understand that, frankly, we don't have comprehensive theories about either one. I know, for instance, that a number of different climate scientists will say, yeah, Earth's climate is essentially the interplay between two fluid bodies, the atmosphere and the oceans. We don't typically, lay people don't think of the atmosphere as fluid. We think of running water and things like that. But in fact, the atmosphere and the oceans are fluid bodies. And if we really don't understand fluid dynamics, if we don't have a comprehensive theory of fluid dynamics, then we are prone to misunderstand how the climate system works. So would you define fluid dynamics and define the greenhouse effect for us, and tell us why we don't have comprehensive theories of them and how important that is to the controversy over man-made climate change?
Well, I think you pretty well covered fluid dynamics. It's the movement of two fluids, the atmosphere and the water, the oceans, rubbing against a irregular surface on a spinning globe unevenly heated by the sun. And this creates what is called chaotic motion. And there's no solution thus far on how to work out what will happen in the future. We can use what we've seen in the past and suggest that this is what may happen, but it's not a matter that we know that it will happen. It's a very complex machine that we live on, the weather machine. Our weather prediction isn't particularly good beyond 14 days. It's often not good beyond 7 days. And to try to make predictions a month and 2 months in advance, we can say, well, this is according to seasons, yes, but it's impossible to predict, for example, when a blue northerner, a sudden cooling from the Arctic, will hit the Texas or hit the Gulf of Mexico. Like they jokingly say, the only thing separating the Gulf of Mexico from the Arctic in the wintertime is a few strands of barbed wire. They can come down the Great Plains at any time. We can't predict that. We can at least well in advance. And I mean the well in advance as being 2 weeks in advance. It's a very complex problems. There are basic equations that have been articulated that have never been solved.
The Napier-Stokes equations among them?
Excuse me?
Napier-Stokes equations among them?
Yes. Yeah. In the greenhouse effect, it's not a mature science. There's much that really needs to be resolved that has not been resolved. The greenhouse effect changes with elevation, and it changes with latitude as you go further north. It changes with the seasons. When water vapor freezes out, it changes what occurs above it. So in the polar regions, in their winters, the greenhouse effect, the effect of greenhouse gases, changes significantly because water vapor, as you mentioned, is the dominant greenhouse gas, and it freezes out in the wintertime in the polar regions. The it's again another very complex problem, but we can observe it, and that's what's important. We're observing the greenhouse effect, and we've been doing it for about 40 years with the advent of satellites. We have difficulty separating natural variation from additional carbon dioxide, but we're observing it, and that's important. And we can observe through satellites atmospheric temperatures and see how they're responding with a change in greenhouse effect. And what we're seeing is that the effect is not increasing significantly or severely, and it is the temperatures are not increasing severely. So the danger of a increased greenhouse effect causing the Earth to become inhabitable is we just don't have any evidence. It's without evidence.
Yeah.
Our evidence is pointing, yes, we will have a modest increase in temperatures, very modest. And overall, the effect of increased greenhouse gases is beneficial because it's greening the Earth. I would also add that without the greenhouse effect, life would probably not exist on the planet, on the land masses, or at least as we know it, because the land masses would go into a deep freeze every night. That would totally wipe out plant growth.
Yeah, kind of like the dark side of the moon. Right.
Yes.
I understand from a lot of my own reading on the greenhouse effect that that greenhouse warming is actually spatially distributed around the world and temporally distributed kind of this way. As greenhouse gases are added to the atmosphere, warming occurs, but it occurs primarily in the higher latitudes, that is, toward the poles, where, after all, it's pretty cold anyway, so a little warming wouldn't be a problem. It occurs primarily in winter, not in summer, which again is the cold season, and so a little warming wouldn't hurt. And it occurs primarily at night, not in the daytime, which again is the cold period, and so a little warming couldn't hurt. The result is that you don't have a significant increase in high temperatures, that is, in the torrid and even the temperate zones in the summer, in the daytime. Instead, you have a raising of low temperatures in the winter, at night, and toward the poles. And that means lengthened growing seasons because the last frost occurs earlier in the spring and the first frost occurs later in the fall. And because you've got sufficient warmth farther north and farther south to be able to farm areas that you couldn't farm at all before. So is that a fairly decent summary of the implication of greenhouse theory as far as the spatial and temporal distribution of warming?
Yes, very well put. We should be very thankful we have the greenhouse effect. And adding additional carbon dioxide, we cannot see where it's harmful. It will increase temperatures slightly, but as you pointed out, predominantly at night, not during the day. and it'll be reduce the winter cold in the polar regions.
Yeah.
Um,
Yeah. And that's pretty good stuff. Yeah. Now, in discussing in your article, in discussing problems with global climate models, you cite former Obama science advisor Stephen Koonin in his book uh, Unsettled, which I read as well. It's a brilliant book and very, very helpful. You cite him as marking two serious deficiencies in climate models. The first is a confusion in scale between Celsius and Kelvin when estimating the influence of doubling carbon dioxide, resulting in significant error. Would you explain that for us? Because a degree Celsius and a degree Kelvin are identical in quantity, right? Uh, but the issue is, where do you put zero? Where do you start from in those? So
that's
just
exactly the
briefly,
issue.
for those who aren't accustomed to talking about Celsius versus Kelvin, especially Kelvin, that tends not to be a part of the lay conversation at all. Explain that for us.
Well,
How does
Kelvin
how does it
starts
affect the model?
zero in Kelvin is absolute zero, as cold as you can get. Zero in Celsius is, I'm going to get this wrong, about not
Isn't it
close to
243
300
degrees
degrees.
Kelvin? Isn't it
Yeah,
243 Kelvin, I think?
273, I think.
Oh, 273. Yeah,
I'm
I
sorry.
believe that's right. I should have looked it
Um,
up beforehand.
yeah, the and there are some very key equations that use Kelvin, where we're talking about absolute zero is the base, and these have been incorrectly interpreted using Celsius as the base, which is 200, I believe, 273 degrees Kelvin.
It is. I just
So
looked it up.
that's you're just making a fundamental mathematical error, and it sounds ludicrous, but you can find these in the models very frequently.
Hmm.
As I said, I found them in the fundamental mathematical errors in the natural gas model on the U.S. energy models, and I can't explain why they occur, but the models have not been thoroughly tested. And when you
Hmm.
that's why you need to test modeling. We have others have discovered fundamental mathematical errors in say the models being used to project sea level rise.
Mhm.
In the thorough testing of models is lacking, and this is a significant problem. Um,
Yeah, there was Ken. There was an article published back around 2004, I think it was, by a sociologist of science by the name of Mayanna Lawson, called Seductive Simulations. It was in a peer-reviewed publication, a peer-reviewed journal on the sociology of science. And in this, she reported the findings of her spending literally years with the climate modeling scientists at the National Center for Atmospheric Research, NCAR, which is kind of the primary place for US climate modeling. And as she spent huge amounts of time with these scientists, she had a lot of different questions in mind, but probably the most fundamental one was, as they do their work, do these modelers keep in the forefront of their minds the difference between their models and the real world? Are they self-conscious of the fact that models and reality are not the same thing? And what she found was that again and again, if she would ask, for example, all right, Dr. Jones, you're telling me that if we added such and such to the atmosphere, the ocean would respond so and so a way, right? Dr. Jones, uh, is that the real ocean or the modeled ocean? And she would get a nervous laugh as the scientist realized, well, no, it's not the real ocean, it's the modeled ocean. What she found was that they had lost consciousness of this distinction between the models and the reality. If we go back to Feynman's talk on the key to science, they had gotten the guess part okay. They had gotten the compute the consequences part okay, but they never got to the compare the computed consequences, compare the prediction with the real world. This is something that I find quite fascinating sociologically, psychologically. Partly, I think it arises from the fact that so many of these climate modelers are much younger scientists, and they did their training in a world in which computers and computer time were cheap, and therefore you tended to spend a lot of time doing models because computers could run them quickly. Whereas before, computers and computer time were very expensive or not available at all, and so when you wanted to set up hypotheses, you had to do your modeling with pencil and paper and do all that math yourself. And so consequently, you were a whole lot more likely to spend a lot of time out in the real world doing the observations to check your model. It's kind of like kids who grow up in video games all the time. They're living life in virtual reality, and they haven't learned to distinguish between that and the real world. Uh, do you see something like that in the modeling community?
Absolutely. They, again, using NCAR as an example, the chief model is there. They don't test their models against reality. They go out and talk to other modelers to see what they're doing.
Yeah,
So they live in a fantasy world. Um, we've recently seen what is called a huge body of studies that come out and assigning probabilities to event attribution. For example, what's the probability that a particular storm, such as Ida, would cause was human caused, and they assign a
yeah,
probability to that, and yet they have no basis in probability, theoretical statistics to assign that probability. To go into why is a little complicated, but the theory, they have to meet certain conditions before you can start guessing at the probability, before you can be reasonable at guessing that what you say is a probability of X, you're somewhere close. They don't know how close they are. They don't know how far away they are. It's just a wild guess. And you have thousands of studies now built on basically wild guesses with no statistical grounding.
yeah, yeah. Now, the second deficiency that Kunin points out in the IPCC models, the Intergovernmental Panel on Climate Change, their coupled model intercomparison project, we're now into the sixth generation of that. Kunin points out that the models don't track the warming trend in the surface temperature record between 1910 and 1940. And Kunin says, and you agree with him, that this is a serious problem for the models. But hey, 1910 to 1940, that's ancient history. Uh, how is it relevant? Uh, what does it matter whether they can track what happened from 1910 to 1940? We're talking about 1970s to the end of this century.
Yeah, that's Kunin's correct. And if you're going to use surface temperature as your grounding, which I don't think you should, then there's no excuse for not being able to track the temperature change shift between 1910 and 1940. I assert that we really should be looking, if we're looking at the greenhouse effect, we should be able to track the atmospheric temperature trends where you have very modest warming. They don't track, the models exaggerate the warming of the atmosphere by 2.5 to 3 times, depending on
Yeah.
where it is. This is inexcusable if you're going to say that the cause of the warming is a warming of the atmosphere from carbon dioxide or other greenhouse gases.
Yeah. Yeah.
And that's what is being
And
claimed.
and the reason that you think that we should not be using surface temperatures as the observations against which we compare the models is what? That they are far more prone to contamination by improper siting of the measuring instruments, by urban heat island effect, by simply the non-representative placement of surface temperature measuring stations around the globe, whereas for atmospheric temperature, especially, say, the lower troposphere, which is the vast majority of the atmosphere in terms of total mass. For that, the way we get that is from satellites, and they're able to measure temperature at pretty much all altitudes, all latitudes, all longitudes, 24/7, 365. So you don't have the urban heat island effect. You don't have the improper siting of the measuring instruments, and you don't have the non-representative sample that you do from surface stations around the world. That I think is really curious to me, precisely because the folks who tend to think of man-made climate change as catastrophic almost invariably want to use those surface temperatures instead of the satellite or weather balloon temperatures or the reanalyses as their observations against which to compare their modeled scenarios, their modeled predictions of where global temperature is going. Uh, Now, the easiest way to explain why they want to do that is the most cynical one. And I think that's to say, well, they have an agenda and those temperatures fit their agenda. Um, let's assume for a moment that that's not the case. Why else would they prefer the surface temperatures?
The arguments that I've heard, the principal one is that's where people live. Uh, I don't accept that as a solid argument on using surface temperature because people don't live in the Sahara very much or extensive parts of the oceans and things like that. Now they use it because that's been traditionally done. Uh, we've when, for example, this 1979 report came out, we didn't have atmospheric measurements of temperature. We had no
Right.
systematic measurements. We had weather balloon measurements and things like that, but they were spotty, very, very spotty.
Mm-hmm.
Uh, and what we're seeing is that a poor method of measuring temperatures, that is surface temperature, is continuing to be used even when we have a far superior method. And you can say this is bureaucratic inertia, and assign no responsibility to it. I call in institutional science. Once it's institutionalized, people don't want to question what has been done in the past and don't want to take changes to what should be done. And that's
Yeah.
I, it's a real problem.
Yeah. Yeah. Ken, we're coming up against the end of the program here. I do have one more question for you. What role would you say our viewers can play in counteracting or countering the widespread notion of catastrophic man-made global warming? What can they do?
Continue to ask, what is the evidence? What is the physical evidence? Not what do the models say. What is the physical evidence? And continue to say that the atmosphere where the greenhouse effect occurs is not warming dangerously.
Yeah.
Okay. I think it's important to question all authority who make bland statements and ask, what is the evidence? If you don't have the physical evidence, actual physical evidence, then you don't have very much in terms of science.
Yeah. Okay, so in other words, you need to go back to Feynman and say, compare your predicted consequences with what you find in the real world. And if you can't show it in the real world, you don't know it. Great. Ken, thanks very, very much again for joining us. I hope all of our viewers will go to sepp.org. That's an environmental policy project. And more about what they do. It's a tremendous organization. You should subscribe to their The Week That Was newsletter, and it's chock full of very helpful information. Well, thanks again, everybody, for joining us tonight. Remember to request 10 copies of one of Cornwall's educational resources to give away to friends. Go to cornwallalliance.org, click on the donate button, make a 100% tax-deductible donation of any size, and in the comments field, write in promo code 21-09 and the resource title that you want. Thanks again for coming. Join us again next week when Greenpeace co-founder Patrick Moore will discuss his new book, Fake Invisible Catastrophes and Threats of Doom, about the science and politics of climate change, the green movement generally, his past in Greenpeace, and why he left it, and his work now in allowgoldenricenow.org. That's allowgoldenricenow.org. Thanks again for coming tonight. God bless.